Welcome to our lecture on the binomial distribution.
A permutation is a particular arrangement. For example, if I ask you how many ways can you arrange the letters A, B, and C, well, I'm listing all the permutations or arrangements. A, B, C is different from A, C, B, different arrangement. You can also do it as BAC or BCA or CAB or CBA. So you really have 6 ways to arrange the letters A, B, C. If using a calculator, you'll see it'll be 3 permutation 3. Okay, now we know 3 permutation 3 is 6. Well, how do we know that? Okay, first, n is how many objects, in this case letters, how many we have. There were 3 letters, A, B, and C. Then we have R, which is going to be the number of slots, the 3 slots. Okay, so let's look at this. We have 3 letters, A, B, or C. So in the first slot, we have a choice. We can put an A, a B, or a C. Suppose in slot 1 we used an A. Now in slot 2 we have a choice of B or C. Suppose we use the B for slot 2. All that's left is C. So there's your first arrangement, A, B, C. If you started with an A and then in slot 2 you put a C, you have nothing left except for a B, which goes to slot 3, A, C, B. Suppose you started with a B in slot 1. Well, in slot 2 you can put an A or a C. Let's see you started with an A in slot 2. B, A. Now all that's left is C. You got B, A, C. If in slot 2 you put the C after the B, so you have BC, you must have an A, that's all that's left. You got BCA. This is called a tree diagram, actually, if you can do it, you'll see. So that's how we know that 3 permutation 3 ends up being 3 factorial. 3 times 2 times 1. So 3 permutation 3 is 3 factorial. If you look at your scientific calculator, you'll see an NPR key. P stands for permutations. N is the number of distinct objects. Before we had A, B, and C. So these are the objects you want to arrange, and R is the number of slots or spaces. So the previous example, we had 3 objects, A, B, C, to arrange in 3 slots, and that becomes 3 permutation 3, which is 3 factorial, which is 3 times 2 times 1, which is 6. The general formula for a permutation is NPR is n factorial divided by n minus r factorial. Thus, when n equals r, then npn is just n factorial. And the way you read a factorial, show it to you, but just let's do it with numbers. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is more than, you see, more than 3 million. It's 3,628,800. So it's a large number. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, or 720. It's actually surprising how large these numbers become. You try 50 factorial, it's going to be an incredibly large number. Let's look at some problems. How many ways can you assign 5 workers to 5 different tasks? Well, that's 5p5, which is 5 factorial. 5 times 4 times 3 times 2 times 1, which is 120. Again, you have a factorial key, so you can just get it directly. 120. How many ways, example 2, how many ways can you arrange 10 different books in your bookcase? And suppose it only has room for 5 books. That's like the slots, spaces. So we have 10 permutation 5. Remember, the second number is the slots. So it's 10 permutation 5. And that turns out to be 10 times 9 times 8 times 7 times 6. The 5, 4, 3, 2, 1 is canceled out by the denominator. But if you just put it in your calculator, you get 30,240. Example 3. How many ways can 8 cars line up single file in front of a toll booth? Again, we're assuming there's space for 8. So it's 8 permutation 8, because there are 8 spaces and there are 8 cars, which is 8 factorial, which is 40,320. The fourth example. How many ways can you arrange 12 guests around the table that has 12 chairs? Well, the chairs are not like the slots, so the spaces. So n is 12, the 12 guests. You want to put them around the table that has 12 chairs. That's 12 permutation 12, which is 12 factorial. And look at the incredible number that is, 479,600,000. And now you can see why so many family feuds occur when it comes to seating family members at weddings or bar mitzvahs or whatever family event you have. So many ways to arrange them, and if your family's like my family, somebody's always going to say, "Why did you seat me next to Jane? You know I haven't talked to her in 7 years." Or why did you seat my daughter next to Ellen? You know they don't get along. Things like that. But look how hard it is. It is, 12 permutation 12 is, more than 479 million. Well, now we're going to talk about permutations and combinations. Permutations, the arrangement of the items is important. Each unique sequence is another permutation. Thus, ABC is not the same as BCA, which is not the same as CBA. You just change around the arrangement, the way it's ordered, and it's a different permutation. So you get generally a larger number than you're looking at combinations. With combinations, ABC, BCA, CBA are not counted as three separate arrangements. It's the same combination. You still got ABC, BC, the same three letters are in ABC, BCA, and CBA. So let's see how this works. So for example, if I ask you how many different groups of three can be selected from 7 people? Let's call the people A, B, C, D, E, F, G. There's 7 people. And now once you select B, D, and E, the fact that they can be arranged 6 different ways, BDE, EDB, BED, it doesn't matter. It's all irrelevant. It's the same 3. So obviously you can get a smaller number. Okay, so that's the difference between a permutation and a combination. Note you have both keys on you can do an NPR or NCR on your calculator. This is the formula for combination. NC, not P, now it's a C. NCR is n factorial over r factorial times n minus r factorial. Notice it's almost the same as the permutation formula, except now you're shrinking it, in fact, by dividing it by r factorial. So that's why we see that NCR is NPR over r factorial. Anyway, you don't have to worry about all this. You have an NCR key on your calculator to solve any combination problem. Make sure you have a calculator that has that key. Okay, so you shouldn't even buy a calculator that doesn't have a NPR and NCR on it. And they're very cheap now. So for example, how many different groups of 3 can be selected from 7 people? Okay, that's really, sampling in general is a combination problem. So if you want to get groups of 3 from 7, again, you don't care how they're ordered. Once you get to 3, that's it. Okay, so it's 7 combination 3, which is 7 factorial divided by 3 factorial times 4 factorial. And if you put this into your calculator, you should get 35. How many different hands can one draw from a deck of 52 cards in a game of 7-card rummy? Again, you don't care about how it's ordered. You just want to see how many different decks from a deck of 52, how many hands of 7 can you get? Okay, that's 52. That's n. Combination 7. That's like your slots. 52 combination 7. That's 52 factorial over 7 factorial times 45 factorial. If you do in your calculator, you'll find there's 133,784,560 different hands you can get in 7-card rummy. Let's try the next example. How many samples of size 6 can be drawn from a population of size n equals 50? Well, this is simply 50 combination 6, which is 50 factorial over 6 factorial times 44 factorial. Using your calculator, you'll get the answer of 15,890,700. And it's very simple. Once you learn how to use your calculator, you have no problem with. The biggest problem you'll have is deciding, is it a permutation or a combination? And that's easy to figure out. Do we care about the arrangement or not? If you don't care about arrangement, and once you have ABC, it's the same as BCAC, then you're basically looking at a combination. Now we're ready to learn about the binomial distribution. The binomial distribution is used when the sampling process works as follows. There are only 2 outcomes. There's 2 possible outcomes. these two outcomes have to be mutually exclusive. We're going to call these outcomes success and failure, even though you might not consider a defective product a success. It's just a terminology to use. Okay, so here are some examples where you just got two outcomes. Heads, tails. You flip a coin, there are only two things that are going to happen, a head or a tail. Or you pass a course or fail a course. If you take a course pass, fail, you're getting a P or an F. Or, as I mentioned before, defective, not defective, dead or alive, hit or miss. So when you have two outcomes only, and they're independent events, which means, and you'll see more clearly in the third condition, the probability of success or failure is constant from trial to trial. For example, the probability of getting a head on a coin toss is the same on every toss of the coin. Even if you got, let's say, 4 heads in a row already, you got head, 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 head. Guess what the probability of a head is on the 5th toss? It's still 50%. Even if you got 10 heads in a row, head, 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 imagine having a 10 in a row, and most of us will say, well, now the probability changed. No, if it's a fair coin, even on the 11th toss, guess what? The probability is still 50%. And again, you'll remember that there are two outcomes because the word bi means two, right? So when you see binomial distribution, you know it's got to be two outcomes. Well, here's the formula for the binomial distribution. This is what you need to know. Obviously, you need to know n, p, and x. Okay, p is the probability of success. Again, success doesn't have to be a good thing. It's just an arbitrary term. Once you know p, you know since there are only two outcomes, you know what n 1 minus p is. Okay, so I tell you there's a 5% chance of a defective product. That means 95% chance it won't be a defective. See, so once you know p, you know 1 minus p. X is the number of successes out of n. Well, if you have x successes, n minus x will be the number of failures because it must add up to n. And here is the formula. It's called the binomial distribution. The probability of x successes is n combination x, p to the x, 1 minus p to the n minus x. And a quick check, when you do this and you write it out, make sure that p and 1 minus p add up to 1. And make sure x and n minus x add up to n. If you do that check, you won't make any mistakes. Well, there you see the formula again for the binomial. The probability of x successes, n combination x, p to the x, 1 minus p to the n minus x. We can figure this out mathematically. The mean or the expected value of a binomial distribution, mu, is just np. The variance turns out to be n times p times 1 minus p. So just keep that in mind. You'll see common sense will tell you that the mean is NP. Here's another problem involving coin tossing. Coin tossing are the classic binomial. Two outcomes, head, tail. The probability never changes, it's always half, 50%. Okay, if you toss a coin 12 times, what's the probability you'll get 6 heads? Okay. Now, but those of you who know a little bit of math know that the expected value is supposed to get 6 heads on average. If you keep doing it over and over again, you will average out to 6 out of 12 tosses. How do you know that? NP. Mu is NP. So 12 times P of a half, you should get 6 heads. That's the most likely outcome. But let's see what the probability turns out to be. Many people think it's 50%. It's not. It's the highest probability, 6 heads, but it's not 50%. The probability of getting 6 heads in 12 tosses will not be 50%. And let's prove it. 12 combination 6. And there you see that in the parentheses 0.5 and 0.5. That's the probability of a head and the probability of a tail, obviously. Or you want to call it success and failure. And notice the exponents are 6 and 6 because you want 6 heads, which means you automatically have six tails. It works out to 0.2256. And by the way, with 100 tosses, we know mathematically mu equals NP, 100 times a half. So you're supposed to get 50 heads. That's the most likely outcome. But the probability of getting 50 heads in 100 tosses works out to only 0.0796. Again, just check the formula. You'll see it's a low probability, 0.0796, even though it's the most likely thing that's going to happen. But you know, it actually happens. You toss a coin 100 times, sometimes you'll get 49 heads, occasionally you'll get 50, sometimes you get 51. It'll average out to 50 heads. That's what mu is, like a long-term average. Expected value, we talked about that. Okay, one more problem. Suppose you know that 60% of the students at CUNY are female. CUNY is the City University of New York. If you're not from, Brooklyn or Manhattan or Queens. Okay, so what is the probability that in a randomly selected group of 25 students, there'll be exactly 15 females? Okay, now notice, by the way, if you want to get mu, which you expect to see, you do take mu equals NP, or 25 times 0.60. That's what the most likely thing should be, most likely outcome. But let's use the binomial. Okay, so x is 15 out of n 25. Okay, and you see the two probabilities, 0.60, that's the probability of female. And we're assuming there are only two categories. Again, we know things have changed, and it's not just two categories. Well, let's pretend there's two categories, female and male. So we have 0.60 and 0.40. Okay, and then we want to know that 15 females. So 0.60 to the 15th power, 0.40 to the 10th power. And again, the 25 combination 15 is obvious. And when you solve that, you'll see the probability is 0.1612. Here's another example. Suppose the probability of passing the organic chemistry course at your college is 40%, which is of course 0.40. What is the likelihood in the class of 45 students taking the organic chemistry course that 22 will pass? Okay, now remember you only need n, p, and x. Well, n is 45. We're asking about 22 out of 45, so x is 22. And the p, let's at 40%, that's 0.40. So it's 45 combination 22 times 0.40 to the 22 power times 0.60 to the 23. As a check, look at the two probabilities, 0.40 and 0.60. It adds up to 1. So, okay, that's logical. Let's look at the two exponents. 22 passed. This 45, that means 23 failed. So we have 22 plus 23 is 45. It has to add up to n. So that's logical. That's where you check your work. So the answer is going to be 0.0572. Let's look at another problem. A machine produces parts that are very difficult to make. Like three-dimensional printers are now being used to make kidneys. Okay, that's difficult. It turns out 1 out of 20 is defective. That's your P right there, 1 out of 20. Okay, and you have to throw those parts out. So I ask you, what is the probability you buy a sample of 10 parts, or a batch of 10 parts? You've got 10 parts. What is the likelihood they'll have 0 defectives? Okay, this is a standard binomial when you see two outcomes and they're independent. So we know P is 0.05. Okay, we know N, because I said that we have a batch or a sample of 10 parts, and we want to know what X equals 0. Okay, so there it is. 10 combination 0, N combination X. 0.05 is the probability of a defective. That's 1 out of 20 is 0.05. You want 0 defectives, so that's 0. And 0.95 to the 10. And as a check, look at the two probabilities of the parentheses. 0.05 and 0.95, they add up to 1. So you didn't make a mistake there. And 0 defectives, 10 non-defectives. The 0 and the 10 as the exponents add up to n, which is 10. So your logic is good. Now look into your calculator. Do n. You've got this, and you could actually do it if you have a scientific calculator straight across. First do the NCR thing, but you don't. In this case, you don't have to do it because 10 combination 0 is 1. You can do it in your head, and anything to the 0 power at the 0.05 is 1. So you don't even have to go crazy with that because that's 1 and 1. All you got to do is 0.995 to the 10th power. That's all you got to do for this kind of problem, and your answer is 0.5987.
All right, here's a problem. This one works a little bit differently. We're still using the binomial, but we have to use it in a little bit of a different manner than before. Suppose we have a smartphone that's produced with 8 critical components, and each one of those 8 parts has a 1% chance of being defective. It sounds pretty good, but we'd still like to know what's the probability that a randomly selected smartphone will not work properly. Okay, if any one of those 8 parts is defective, it won't work properly. But think about it. If 2 of those parts are defective, it won't work properly. If 3, if 4, if 5, and certainly if all 8 parts are defective, it won't work properly. So this is a little bit more of a complicated problem where you can get the probability for each of those situations, the probability that x is equal to 1, is equal to 2, is equal to 3, and then you add them all up because those are mutually exclusive, and the sum total of all of those probabilities is the answer to the question, what's the probability that a randomly selected smartphone will not work properly? We're going to show how that works and then hopefully figure out a hack to do it a little bit differently and a little bit easier. Let's take a look at the work here, what we have to do to solve this problem. The probability that the smartphone will not work properly is the probability that there's one defective, as you can see, 0.07457, plus the probability of having 2 defectives, 0.00264, plus the probability of 3 defectives, 0.00005, plus the probability of 4 defectives, and this number is so small that it's in effect 0. And the same thing holds for the probability of 5 defectives, 6 defectives, 7 defectives, and 8 defectives. And when you add up all of those binomial probabilities, you have 0.07726. So the answer to the question, what's the probability that the smartphone will not work properly? It's 7.73%. 7.73% of the phones coming off the assembly process will not work properly because of defects in these 8 components, possible defects, probable defects. Now take a look at something else. The next item here, what is the probability that the phone will work perfectly? Well, that's easy. We don't have to get a million probabilities and add them up. The probability that the phone will work perfectly is the probability of 0 defects, which we haven't done yet. It's not one of the probabilities on the right side of the screen. The probability of 0 defects, applying the binomial formula, is 8 combination 0, which is 1, p to the 0, which is also 1, and then the only thing you actually have to compute, 0.99 raised to the power of 8, which is equal to 0.92274. Well, look at that. That makes my job a lot easier. Instead of getting all of those binomial terms and adding them up and getting the sum of all the binomial probabilities of the various ways that we could get a defect. We could just get the probability that there's no defect, the phone works perfectly. And that's not what we want, of course, but if we take 1 minus that, 1 minus 0.92274, that's everything else. That's the probability that it will not work perfectly. And it turns out 1 minus 0.92274 is indeed 0.07726. So this is a kind of a problem where you are asked for a probability, you know the binomial distribution is involved, but you have to figure out what you want to compute to make life easier for yourself, and then work with that in order to get the answer to the problem. We'll see another example of this coming up.
Let's look at a problem. Let's pretend an air conditioner made by a certain company is made of 20 distinct parts. And let's assume each part independently has a 0.004 probability of being defective. That's another way of saying 4 chances in 1,000 of being defective. So you're going to assemble this 20 different parts, and each part has a 0.004 probability of being defective. What is the probability that a randomly selected air conditioner will not work perfectly? What does not working perfectly mean? That's the trick to this question. Not working perfectly means, well, with one defective part, it doesn't work well. How about if it has two? Also doesn't work well. Three also doesn't work well. How about if all 20 don't work? Well, you can have a very bad air conditioner there. All 20 parts not working. All right, so now we know P equals 0.004, N is 20, and I ask you, what is the probability that it won't work well? So you're really looking at that it has anywhere from 1 to 20 defective parts. And I'm going to show you a trick how to solve this problem. Well, the best way to solve this problem is not to solve it for not working, because what does not working mean? It could have one defect, it could have two, it could have three, it could have four, it could have five, and certainly won't work well if all 20 parts are defective. Let's try to use a different approach. Let's first solve for the problem of what is the probability that it works perfectly, and what does working perfectly mean? If something consists of 20 parts, it means you have 20 parts, all 20 are good, and 0 defectives. So that would be the solution for a perfect air conditioner. 20 parts, 0 defectives. So that's 20 combination 0. 0.004 to the 0 power, that's the defective side, you have 0 defectives. And 0.996, that's the probability each part works perfectly, to the 20 power, because you want all 20 parts to work perfectly. That works out to, remember, the 20 combination 0, just 1. 0.004 to the 0 is 1. All you got to do is 0.996 to the 20 power, you get 0.923, and that answers the question of the air conditioner working perfectly. All 20 parts are good, no defectives. Now you want to know, well, but that wasn't the question. The question is that it doesn't work well. What does not working well mean? At least one defective. Two, certainly not going to work well. Three, so you just take 1 minus the 0.923, and that's 0.077, and that answers the question that the air conditioner does not work well. In other words, there's a 7.7% chance that a randomly selected air conditioner made by the company will not work perfectly. Now, how do you improve quality? That's the reason we're doing these problems, to let you think logically. Of course, you can try to improve the defect rate and change it and work hard on that. But what many companies have discovered, reduce the number of parts. Today, you can make a computer out of like 15 parts. The fewer parts you have, the less likely something will not work well. So now you have a key idea regarding quality control. Try not to make things with fewer parts. And of course, you try to reduce the defect rate for each of those parts, and then you'll have a better product.
Once you have studied the material, find as many problems as you can. You'll find them in all different areas of the website, and you'll find them in all different kinds of books. And we even have it in the boot camp. Do lots and lots of problems. You do your homework problems and anything else you can lay your hands on. It will become second nature to you.